So we have Samir to give us our third lecture in the series.
Okay, so let me pick up again from where we were yesterday. Today I'm going to give you an impression of what I think the solution to the puzzle is. So far we've been talking about the puzzle itself. I will not be able to talk about everything which I had initially planned to say, to talk about, and so I may not get to things like firewalls and some other things and wormholes in much detail that I wanted to talk about. But I'm here for the whole of this week to the end of the workshop, and so you're going to catch me and we can talk about those things. Okay, so just to summarize where we were, so we were just had this walking process. You have some kind of a star, it collapses, makes a black hole, and then you get these entangled pairs being produced, and because they're entangled, you have some problem. And so what's the simplest solution? So up here, the simplest solution is that, in fact, instead of having this thing where all the masses go to a point, and then you have vacuum around here, it's the vacuum which was unstable. That's when you can get negative energy particles, you have positive energy particles, you have a problem. Why doesn't the black hole actually behave more like a star? If it was like just a solid ball or a ball of some fluff or something, then you would never get a place where you would actually have negative energies. It would more like the Earth or something, and then you would have a problem. So why is this not easy to do? Why do people think the black hole has to be like this? And that has a long history which all goes into the theorem, black holes have no hair. So what does that mean? Why do black holes have no hair? Why can't you just change to this if you're having so much trouble? And that you can see by a picture of what a black hole looks like in general relativity. So let the vertical direction be time, and this is angular space, this is the radius near the angular coordinates. So far away you have light cones, and you know the light cones look like this. So you can only travel inside the light cone because you can't go faster than the speed of light. So as you come close to the horizon, which is drawn by the dotted line, this is the R equal to 0, this line. If you have the light cone start turning a little bit inward, so you can see out here, you can still go in, and you can actually also come out, but you can see it's a little more difficult to come out. By the time you come right to the horizon, if you can of course go in, but if you try to fly out, you really can't get a bigger R. You stay stuck at the same place. You try to get out, but you really can't. And if you're further inside the horizon, the light cone has completely turned inwards, so you're forced to go further inwards, and the star has to keep collapsing, so it all has to reach R equal to 0 and get crushed. So you can see in general relativity, once you come inside the horizon, you just can't stand there. You have to keep going in, and if you want to violate that, then you need to really violate the very basic belief we have that nothing can travel faster than the speed of light. So you can see, even apart from that, even if you try to make something which is pretty close to the horizon, like if a star had a surface out here, it's also very difficult, right? Because the guy is still trying to, you have to go very fast and just stay there. It might be still very difficult to stand even just a little bit outside the horizon. So that's the intuition that once you come close to a black hole, you're going to get sucked in. So we have to make that a little more precise, because if you want to actually replace the black hole by some kind of a ball, then that's the problem we are really fighting. How do you fight these pressures? Why could nobody find a solution before which would really stand there like a ball, because obviously that would solve everything for you. So to make that more concrete, you have something nice called the Buchner's theorem. Suppose you take a perfect fluid, and the fluid has a radius which is less than 2¼ m. So 2m is the horizon. Suppose you go up to 2¼ m, so I drew it like this up here. Even there, if you try to make any ball of fluid which is at 2¼ m, at first you might think that's okay, it's not inside the black hole, it can stand, but actually it can't. So if you try to make a perfect fluid ball whose radius is less than 2¼ m, the ball will have to collapse. And how do you prove something like that? Well, the proof is very simple. You take any particular shell, impedance per shell out of this ball, and the shell has to have a pressure gradient, more pressure inside than outside, so that you get pushed to counter the attractive force of gravity. Right? So the pressure has to keep increasing. Like if you look at the sun, the pressure is 0 at the surface, but then it's more and more inside, because each shell has to be supported by the more pressure inside and less pressure outside. So if you actually solve the equation dp by dr equal to the attraction of gravity at each place, and you integrate that, you find before you get to the center, the pressure goes to infinity.
Is it classical calculation?
Yes, completely. Just put in the Oppenheimer-Markov equation. So in fact, if a fluid has a radius, a ball has a radius less than this, then it's actually going to not be possible. It will start collapsing, and of course, once it collapses, it gets worse and worse. It's all going to go to the center. So this is really, you can just get an intuition. You're trying to prove the no-head theorem, but this is where the problem comes from. Things just can't seem to stand, and therefore they have runaway collapse, and you get the black hole. It's important to understand the no-head theorem is not just classical, but actually also quantum. And that's actually going to be very important for us. So when we say we have the vacuum here, it's not just a classical statement that the metric looks like the normal Schwarzschild metric, which of course is the vacuum solution to gravity. Even the quantum fields which are out here have to be in the vacuum state. Like this room here is in the vacuum state. Forget the air here is in the vacuum state. The quantum fields here are in a certain state where their oscillators are really all in the ground state. Okay? And the same no-head theorems which work classically actually also tell you the whole quantum vacuum is in the vacuum state. And what is that? How do you get that? So you take a scalar field, you solve box phi equal to 0, and then the solutions to that, if they are called Fk, you know this is how you expand the quantum field. Fk multiplies some creation and annihilation operator, and Fk star multiplies the creation operator. So in fact, when you write the quantum field, let's say a quantum scalar field, the function, in terms of which you expand it, are actually solutions of the same wave equation that you would have solved for your classical problem anyway. Right? It's the same equation. And once you get this, if you get solutions of these guys, then say you solve box f equal to 0, you expand a quantum field, and if you want to solve it in this, because spherical symmetric situation, suppose you have a star, you would write your answers as some f of r, some y lm of theta phi, e to the minus I omega t, and once you've got these solutions, for every such solution, you put a creation annihilation operator, and that's the complete quantization of the fields around the star. That makes sense? That's how you quantize them in the vacuum, so you can quantize them around the star. If you take the state which is killed by all the AKs, you have the vacuum solution on the star. No more particles than what the star has. And if you act with one AK dagger, you take the star plus one particle. You put two AK daggers, you have star plus two particles. That's the full quantum theory around the star background. Good. But now what turns out, so all these states are then given by acting with more creation operators around the background you have. But when people started doing the same thing for the black hole, they found that the solution to F that you get around a metric which actually has a place where the GTT, you remember, goes to 0, the metric changes sign here. In that situation, the f of r actually always diverges. There is no normalizable solution to this equation. So in fact, it's the same as the classical problem, that you cannot actually find any perturbation classically, but the equation is the same classical equation you solve for classical physics really goes into quantum physics, and that's why you can't take this black hole and say, I will add one more particle to it by putting an AK dagger or several particles and have them stand there. Nothing can stand there. Everything you try to put near the horizon, it either falls in or flows off to infinity, whereas it is an unstable place. Nothing stays there. The whole thing cleans out in a time of order, whatever the crossing time, 2m for the black hole, and you go back to the vacuum. So that's really the no-head theorem. This state here is not just classically in the vacuum, it is quantum mechanically in the vacuum. And the no-head theorem has been with us for like 40 years, and so if you have to get this black hole, you can see why the problem is so serious, because then you get the pair creation that also people have stared at for 40 years. You have to get that in this background. It's just a stretching of slices. When you stretch slices, vacuums change. Nothing you can do. It's very, very robust. And then you get the entanglement, and then you have seen the problem. So people just couldn't shake any piece of this for 40 years, so obviously this solution has to be somewhat surprising. So this is the problem. And now let's see what the principles are. So now we go to string theory. And string theory has certain kinds of black holes. We wouldn't actually need the details because I wasn't going to talk about them. But you can make a black hole by putting various kinds of brains together. One of the most standard black holes was made by Strominger and Waffa, taking D1 brains, D5 brains, and momentum charge. But you don't actually need to see this for the purpose of this time. So what Strominger and Waffa did, that work was actually very nice. It's from 1996. So they said, look, we don't know anything about the black hole in string theory. It's obviously as complicated or more complicated than what you could see in general relativity. But let's look at supersymmetric black holes, which have mass equal to charge. With supersymmetric states, you have a nice property. As you change the coupling constant of the theory, the state has an energy which cannot change. It's just a PPS state, its energy won't change. So first, let's look at how many states we can get for a certain amount of charge. You take a certain number of D1 brains, D5 brains, and momentum charge. You go all the way to zero coupling. Well, now you just have D brains in flat space, and you can count how many states they have for a given number of brains. So for a given mass and charge, at weak coupling, there's certainly no black hole or anything, just brains. You can count how many states you have. You can get an entropy by taking the log of the number of states. When you increase the coupling to be a strong coupling, well, now the gravity is there, and these brains have some mass, so you think they'll create a horizon, and you'll get this kind of a black hole.
And of course, if you know how much mass and charge you have, you put those equations with general relativity, and you get a surface area for the horizon. And they said, at least are these two things equal? And miraculously, they found indeed they are equal. So it's a very beautiful result. You can really at least at weak coupling, if you count what the states look like, and you get a number, and the log of that is the entropy. And then there's this funny area kind of entropy that we associate to black holes in general relativity from the work of Bekenstein, and the two numbers are exactly equal. And this work has a history before. I mean, Susskind started doing something, and Ashok did something nice with two-charged black holes. And then with this black hole carrying three charges, Samir found an exact agreement, and so it works out beautifully. So now the question is, well, the picture of the black hole they're still using is this. At strong coupling, all the brains have gone to the center, and you have a horizon, and that's the area you count. And for the purposes of the information paradox, we're exactly back where we were. We still don't have a solution to the problem. So what we really want to know is, the missing step is, what do all the states that Strominger are accounting, or any other black hole in general that you would like to think about, what do they look like at strong coupling? So at weak coupling, they're just some brains, and there's no black hole, there's just some weak gravitational fields, and nothing happens. But in string theory, you can dial up the coupling. You have a coupling constant little g, which comes from the dilaton field in string theory. And you can imagine having a dial in your hand, you put in the computer all the properties of string theory, and you take a state with, let's say, 100 d brains, and with coupling g equal to 0.001, it's just a weakly coupled d brains, you know everything about them. And then as you increase the value of the coupling g, the wave function of these guys will change. And you can ask when the g goes to a big value, when you actually are expecting to get a black hole, what is the wave function? It's a completely technical problem, and in principle it should have an answer. And what happened is, that's the game that we try to do in this whole story of fuzzballs, and somewhat to one's surprise, this is not what you get. So what happens as you increase the coupling, the states actually keep fluffing up. So as you increase the coupling, instead of gravity making the guy shrink in, the way the state behaves is that actually the thing keeps fluffing out, and always tends to be a little bit bigger than what would have been its horizon size. So the guy never actually falls inside its horizon. If the guy actually even once fell even a little bit inside the horizon, it couldn't really stay there, because then the night cones have turned inwards, and as we see, string theory also doesn't break causality, or nothing can travel faster than the speed of light, even in string theory. So once you went inside the horizon, you had the problem, you would keep going in. But I'm telling you that the guy stabilized to a size just outside the horizon, maybe a few Planck lengths outside the horizon, just a second. And so then you have to ask, how do you beat this Bucadil's theorem, which told you that if you come even at 2¼ m, you have to get sub 10. So what is the nature of these fuzzballs? How are they able to stand there when all the classical Mohair theorems and all the work of all these years just kept telling us nothing can stand just outside the horizon? Yes, please.
Is there a tunneling probability for them to go inside the horizon?
I will talk about tunneling in a minute. Okay, that's going to be very crucial to a lot of things. Yeah. But yeah. We'll talk about that. You should ask that question again in maybe 20 minutes. So anyway, so what we found is that every time you take a bunch of strings, so this is where the whole thing came up. It's not like a conjecture from scratch that you would like everything to be like a ball. Well, that's more like a wish list. Everybody thinks it should be like a ball, then there'll be no problem. We started at the other end. We actually looked at states of string theory, the very simple states you can start with, which are states made of just two charges. You can just take d1 and d5, for example, you don't have to add the p yet. And then actually you can make all the states. It's called a two-charge black hole. It's a very simple black hole. You can actually make all the states, and you find all of the states actually are like these balls. I'll explain this picture before. None of the states actually are like this. So that's interesting. And then people started working with this three-charge black hole with d1, d5, and p. And in fact, very interestingly, you can even do non-external black holes which also radiate. And that's what's called the JMART solution. And here, Vishnu Jejara is one of the people in JMART. He's a chain JMART. And so you can actually keep trying lots and lots of things, which are two-charge black holes, three-charge black holes, four-charge black holes, non-external black holes with rotation. So all kinds of cases that you do, people have never found a single case where you actually create a horizon. So starting from the string theory side, you seem to get some completely different structure where you expect to get a black hole, you are not getting a black hole. So the theory seems to be taking care of itself, which is nice because, as we said, this way doesn't allow remnants. And if remnants are not the answer, then unless you do something very non-local, and I'm going to argue at the end, string theory also doesn't have that kind of non-locality, then this theory had to save itself somehow, and it seemed to be saving itself by not actually allowing a black hole to form. But that really leaves us with the real question. Firstly, how does this guy stabilize itself? Why is it not collapsing? Why was this kind of solution missed in the earlier Mohair theorems? And secondly, how do you get here? Normally the collapse of a star looks so classical. semi-classical. A ball is there, it's shrinking, just goes in, you can put in a computer, and the GR people have been doing that for 50 years. And you have to ask, what breaks the semi-classicality and converts the collapse that we are taking here over to something which goes to something completely different. So these are the two questions that I have to answer in the any time. So again, as I said, the first ball is supposed to be maybe just out to the horizon. How is the guy stabilized? How did escape the theorem black holes have no air? Why did just not collapse to a black hole with the Wilson's theorem? And so instead of actually looking at a first ball solution, which obviously a little complicated because there is a whole string theory exactly and rigorously, I'll actually take some toy examples which will extract the essential properties of these first balls and show you how these guys stand up against that. So here's a toy example. Take the metric which is called Euclidean Schwarzschild. So I have to first tell you what is Euclidean Schwarzschild. So the Schwarzschild metric looks a bit like these last 4 lines. In fact, if you look at this, R0 is what you think of as 2m. I just call it R0 to not keep adding n. That's not really the mass involved. So up to here, if you look at this is a Schwarzschild solution, except I've changed the sign of the time to also be a plus, which means I took t to I tau, which means I made it Euclidean, and so these 4 lines are what are called Euclidean Schwarzschild. There's also a solution of Einstein's equations, because if you take t to I tau, it's only a symbol. So if your r mu nu was 0 before, it will be 0 now. If you actually add a completely orthogonal direction to it, just slam in a minus dt squared, it still satisfies Einstein's equations, because there's no mixing between this side and this side, and this is a solution, it's a vacuum solution. Adding a flat space piece actually solves the 5D Einstein equations. So this is what is called Euclidean Schwarzschild plus time. Okay, there's no charge here anywhere, but let's take a look at the nature of this solution. Now if you just look at Euclidean Schwarzschild, what does it look like? So now the time, I have made Euclidean, but I will also make it compact. So you make it into a circle. And then you find if you make it a circle of the correct radius, this much radius actually, then in fact this entire Euclidean Schwarzschild metric, it has the shape of a cigar, this side is infinity, it comes up to what would have been the horizon, r equals r0. But there's no place inside the horizon. With all signs positive, there's obviously no inside the horizon where the metric changes sign. As you come to r equals r0, for this particular choice of radius, it's actually completely small. So it's like the tip of a cigar. So is the Euclidean Schwarzschild solution familiar to many of you? If you learned about thermal field theories in the context of black holes, this is what people did to derive, for example, the entropy of the black hole. So the work of Gibbons and Hawking. So here's just a manifold which is compact, and if you don't want to think about details of all this, then don't worry about it. It's just a cigar like this. And it is at all different angles. If I draw the theta, suppressing the phi because it's a theta equals pi by 2. If I look at all possible phi's, then all the different angular directions are like this. So the picture here is I have my normal space-time. I have one extra circle, it's 5-dimensional space-time. I have one extra circle. Circle is everywhere at infinity, just circle of fixed size. As I start coming closer to the middle of this room, the circle size becomes smaller. In the middle of this room, I've taken a whole ball, cut it out, and thrown it away. It's not part of space-time. Then you might say, if I come near the surface of that ball, where will I go? I'll fall into nothing. Well, it's not like that. Everywhere there was an extra compact circle sitting over me, which I didn't notice. As I come close to the surface of this hole I have cut, suppose here's the boundary of the hole, the circle pinches to 0 size to make a cigar. So in fact, space naturally closes off smoothly. If I came from outside, close to this hole which I cut in the middle of this room, I actually come here and smoothly go out like this. And from every direction. But
you throw away more,
to throw in the interior of the
the
hole.
boundary remains.
Well, so the boundary would have been a problem, so I could have worried if I come here, do I fall in? But I don't, because if I pinch the compact circle here, it's a smooth manifold. It has a non-trivial topology because there's a sphere inside which is non-contractible. But there's no boundaries in the sense it's geodesically complete. It's not like there's a hole I can fall in. If my geodesic comes here, it goes right back here. So geodesically complete but a different topology. That's very important. It has a non-trivial pi 2 now. There's a sphere which will not shrink. But that's the geometry of this space. It's a solution of Einstein's equations. It's there. Okay. So let's take a look at this solution. Why should this solution be a little interesting to us? Even though I have an extra compact circle, this tau, now my normal 4-dimensional space-time, this is my time and this is my space. You can see far away it's going to flat space. Minus dt squared, far away this is dr squared, r squared d omega squared. Flat space far away. This is my extra compact circle. It came from original time, but now it's just an extra circle. At infinity, its length is just some fixed amount. As you come closer to r equals r0, you can see its size is going to 0. That's the fifth dimension. But this is the 5th dimension now. These are my normal 4. So if you have a 5th dimension like this, I suppose you're familiar with the following idea. You can do what's called dimensional reduction. The size of that circle can be thought of as a scalar field living on my remaining dimensions. When the size of the circle is big, the scalar field is big, and when the size of the circle is small, the scalar field is small. So this is really ordinary 3+1 dimensional physics with one scalar field. Okay, so if it's looking like, I should look at it in that way, 3+1 physics with one scalar field, and somehow I found a solution here which is somewhat non-trivial. Because in this solution what I'm going to ask you is there any energy density? Now there's a 3+1 gravity and has a scalar field. Will the scalar field have any energy density? Probably yes. If it has energy density, why is the whole thing not shrinking? This time independent. So let's see if the question is clear. I have given you a scalar field. There's obviously energy density to the scalar field. Normally if I just give you some energy density like a ball of dust, it collapses. Why is this guy not collapsing? That's what we want to ask. So as I said, first I'd like to look at this in terms of dimensional reduction. So size of the compact dimension, the fifth direction, the tau direction, you write as e to the phi. The numbers don't matter. This is technicality of how you do dimension reduction. So you write this as scalar phi encodes the size of this compact dimension. This just comes from that. And the metric of the 3+1 dimensions, you have to scale it a bit to make it satisfy the Einstein equations. This is all standard dimensional reduction. But if you allow me to do that, the metric in the 3+1 dimensions looks like this. There's a metric like this. And the action now of the whole thing is 3+1 dimensional Einstein and a scalar field. It's all natural. All the things have the correct sign to be the normal action for a normal scalar field and normal gravity. So we're really doing ordinary physics here. And yet this thing is not collapsing, and we have to ask why. You compute a stress tensor from that action. It's a normal one. It has all positivity properties. So all energy densities are positive, and yet the guy is not shrinking. If you compute the entries of that stress tensor, because you know exactly how the phi is changing with position, so you know all the gradients of phi, you can put them here. You can compute all the components of the T mu, and the T mu components are minus rho is diagonal. You have energy density and then the pressures. Right? That's what the stress tensor looks like. And the entries look like this. They all have the same magnitude, and the function f is like. But here's the interesting thing. Actually, if you look at any of the pressures, and you like to look at the energy density, let's say, it's positive. And in fact, as R goes to R0, as you come to the tip of the cigar, the energy density is actually diverging. It's a very, very high energy density shell. It's a shell, as you come to R equal to 0, energy density is diverging, and yet the shell is not collapsing. Okay, why is it not collapsing? Well, if you look at the pressure, PR, the radial pressure, that is also diverging. Okay, so if you look at the shell at any given location, in the picture, let's say look at dimension reduction at this location, there is energy density from all this scalar field, and there's more pressure on the left than on the right, so there's a gradient of pressure, you have pressure gradient, it's supporting it, and that's fine, pressure gradient is supporting it. But the pressure is actually going to infinity. Okay, so let's look at Bugdal's theorem. Once Bugdal found the pressure somewhere was going to infinity, he said the solution is sick. Let's throw it away. But here the pressure is going to infinity. So is the solution sick? Well, obviously not. As seen as a 3+1 dimensional solution with a scalar field, it obviously looks crazy. The components of the metric are diverging, the components of the scalar field are diverging, everything is diverging. But just because all the numbers have been made to work exactly right, the full solution in 5 dimensions is completely smooth. And so this is how all the fuzzball solutions work. So the way they work is, if you just take 3+1 dimensional physics, you're never going to have any violation of the black hole Moore-Head theorem. You cannot get any solutions. What's really going to happen is that in string theory, you also get to get extra structure. So suppose you have extra dimensions, 6 extra guys. Now you can take these extra dimension circles, and of course extra dimensions have been with us for many years. From the work of Gross in 1980, you know, there can be extra dimensions. If you do perturbative use of extra dimensions, you just get a scalar field. For example, G55 can be called phi. And then that's as good as starting with a scalar field. So that way you get nothing. Same problem of Moore-Head that you always had. If you have extra dimensions and use them non-perturbatively to change topology, that is the one case for Moore-Head that will never be checked. And what you actually, it's very difficult to imagine how you would make it, because all the numbers are not precise, you wouldn't actually get the guy to stabilize. But because we start from the other side, we start from full string theory with all its numbers, whatever they are, we actually took some d-brains, and we just did a technical work of finding out what their structure looks like at strong coupling. You automatically land up with a solution which is completely regular, satisfies all the smoothness properties that you could think of, and which has this kind of structure. So in fact, the whole in the earlier Moore-Head theorem was extra dimension with non-trivial topology had never been included. And all the fuzzball solutions are exactly that. So you take the extra dimensions, there are a large parameter class of solutions. In fact, for the simplest case of two-charge black holes, you can write all of them down. You can quantize them and count them. Okay? And Richiko did that up to some point, and you find exactly the right number for the Eigenstates entropy. All states are accounted for. You can actually prove that under the solutions. So you can prove that for the two-charge black hole, two-charge external black hole, the simplest black hole you can make, all the solutions are of this kind. And they account for the entire entropy, and not a single solution will be of this kind. Yes?
So does this mean that a star before collapse would also correspond to something with non-trivial topology?
I'm going to come to that in a second. And what we're going to argue is if a star is trying to collapse, there will be a tunneling, exactly the kind of thing you just were asking about before, to these solutions. And the tunneling rate will be so high that before the guy can actually reach 2m, it would actually become a linear combination of this. That's the conclusion. So right now we're just trying to compute before any dynamical process. We're just asking what are the time-independent solutions with the given mass and charge in string theory at strong coupling. So that's the new question you're asking. At weak coupling you can count them, but that doesn't tell you the structure of the black hole. But if you look at very simple states, there's actually a way of calculating what it would do all the way at strong coupling. So the part of string theory which we are now trying to use, which maybe wasn't there in our particular string theory of the past, is we want to go to strong coupling and have a large number of objects, like d brain should be 1000, not 1. And in that situation, what is the nature of the wave function? Is it a point, or is it a ball of size 1000? That's the scale with the length. And you find it does scale, and the nature of the structure always is that you get these non-trivial topologies, and those are all the purple solutions. And the number of those solutions in that topological class, they account for the entropy, would be the conjecture. You can't do it for all kinds of black holes, it's technically very messy. But for very simple black holes, you can do left, right, everything you can do, and that's what the answer looks like. The conjecture would be the same for all other black holes, and many people are trying to work on that.
Always your black hole, like they don't have anything inside, it's just gone.
That's
it's
right.
not a part of the space.
That's right. So you should imagine taking this region inside and throwing it away. And then you close the space-time before it comes to this boundary. So that's why I sort of draw it like this. This is not part of space-time. As you came in, the whole thing sort of pinched off here, and so this is like the tip of a cigar which I'm back to top here. But in different directions it comes and pinches off slightly differently. And that's where the entropy is.
All the matter would be like so just distributed on this.
That's right. So let me just draw that. That's a good question. You can ask where the energy of the black hole went. And the energy actually went in the curvature of the tip of the cigar. It's all in the geometry. So if you take this as the ball that you cut out, so obviously it's a little more complicated toy example I drew. This guy, when it actually collapses, what it makes here is actually a Caruso-Klein monopole. It's a slightly more difficult structure than what I just drew like a cigar. It's a Caruso-Klein monopole where also a circle shrinks. But because it's a monopole, it can either come with a plus sign, plus charge, or a minus charge. You can have a monopole and anti-monopole. It's a smooth solution of gravity. And now as you come from different directions, suppose here you had a monopole, and here you had an anti-monopole. If the compact dimension is size the Planck length, the whole structure here is size Planck length. Anti-monopole has just one scale in it. So I'm coming from different directions, and I can put a plus or a minus at different places. And so for every Planck cell on the surface of this sphere, I have one bit, like plus or minus sign to choose to get all my possible solutions. And if you give me roughly one bit per Planck area, you would get the entropy that you're looking for in the black hole. So that's very roughly as a crude picture of where all the solutions are. Yes.
Would this physical picture come up no matter what kind of black hole you're considering? So
that would be the conjecture.
okay.
It's not like you can do. So the problem is if you give me a solution which is very far from extremality, string theory works best when you start with extremal, go a little away from extremality because you get the protection from SUSY and you can do it well. So for completely neutral guys, we just have some solutions which are maximally rotating because rotation also is like a charge in some sense. And so you have to get protection from something to keep yourself accurate, to be not have a quantum correction problem. But in every kind of boundary people have tried, like maximally rotating and neutral or only charges and no rotation, those things have been done also now. So you always get this. So where you can do it, this is what you get. Right now I'm making a crude picture, I'm just saying Schwarzschild, but Schwarzschild with all these things, nobody has actually been able to actually do this. So I just wrote you a toy picture, but I didn't put any charges, I didn't put any rotations, I just said it comes the same way from all directions. That's why I made a toy model of this. But really what you're expecting is that as you come in, so if you look at the simple two-charge solutions, you really get KK monopoles and anti-monopoles, and as you go to the more complicated ones, they have more monopoles. That's the picture. And that's the kind of work that Pina and Wander are doing in great detail, we're putting more and more of these pieces. But you can roughly see if you come in different directions and you pinch on the circle with either a clockwise or anti-clockwise twist as you come in, then you roughly get 1 bit per Planck area of the surface, and that's what I'm trying to draw by this kind of awful picture. And so if you go back and look at the original picture of the black hole, this is flat space far away, then you come here, and then there was a horizon, and then inside was a sky. This picture makes sense? This is R equals infinity, then this is the, R equals 2m, 4, R equals 4m, and so on. This is R equals 2m, and this is inside the horizon, and this is R equals 0. And now what you're getting is far away still have flat space, and this was R equals 2m, this was R equals 0. The entire inside of the black hole is not there, and out here you have this thing just closes off, just outside R equals 2m, just a little outside R equals 2m. So that's what you actually. So it's difficult to draw it because it's in so many dimensions, so all these pictures I'm drawing are very crude. But what is happening is if you actually take some brains of string theory and actually compute their wave function, they never actually generate a vacuum region where the light cones have actually turned over. So actually that is very important because as far as I would like to believe from string theory, even though string theory has extended objects which are long strings, you can never actually break locality or causality in string theory, would be my personal belief. So even if we have a long string like this, if you shake one end of the string, the information goes to the other side only at the speed of light. So I think you can't really break causality. And if that is true, once the light cones have turned inwards, you really can't get out. So once you make a closed trapped surface, which is what I was showing you earlier, once you're inside a certain region R equals 2 and light goes inwards, even with string theory and extended objects, you should draw yourself a string which goes from light cone and sort of leaks out and then is happily back at infinity with the information. So really what has to happen is before the light cones ever turn over, something has to intercede and convert yourself to these animals. So that's what I want to show you next. What process actually intercedes in the semi-classical process where it would seem the star should smoothly go through its horizon and continue going and the light cones will dip and then of course you can't get out of the problem.
At what point during the evolution do you think this kind of thing would happen? I mean, just before the thing has entered within its Schwarzschild?
I would think it is just when it's about to reach its Schwarzschild radius. I'm going to give you the reason now. But this is all the whole gray area which we would like to know better. So if you say it should be a little different, it could well be true. So that's because now we're talking about dynamics, and in the dynamics we're only going to make conjectures based on the rough picture we have of fuzzballs. We can't actually make all the fuzzballs and superpose them to do the general dynamics because that's too complicated.
Do these pictures they also reproduce properties of black holes in the sense, for example, they can recreate, for example, the Hawking radiation and stuff and so on as well?
Yes, so I will actually talk about Hawking radiation. Not to mention, let me talk about it now. For Hawking radiation, the black hole must be non-extremal. If it is already extremal mass equal to charge, it doesn't radiate. So the only case for which that has been done, for which it works out very beautifully, is the J-Mart solution I just talked about. So you have one solution, it's not very typical, it's very highly rotating. But take that solution. It's one particular state of D1, D5, and P branes, so you know it's one of the Strominger-Markov states. For that, you actually know the metric. It's not a black hole, it's like this kind of thing. From this, you can, because this one is non-extremal, you can actually compute the emission from this. It was done by Myers and company. It's the whole group that did this calculation. And then if you compute how much this radiation is, you find exactly agrees with the Hawking radiation down to the last factor of 2 and pi, which you'd expect for this particular non-generic state, based on the CFT gray body factor calculations. So you actually get an exact matching of the whole spectrum of emission. So what you would have is normally you thought the radiation came out in pairs, and this creates the information problem. Now you don't have any horizon, you don't create that kind of pairs, but you have an unstable regions here which actually emit, which is what's called ergo region emission. And the spectrum here matches exactly down to the last 2 and pi, what you wanted for Hawking radiation from this particular microstate. So I can show you in more detail later on how that works out. But for me, this has actually been a very convincing piece of the fuzzball story because it really tells me that what we think of as Hawking radiation really comes from this fuzzball kind of structure. The whole spectrum is a huge long expression. You get exactly the same answer from the CFT calculation and from this particular fuzzball's gray body emission. So it's nice to see that, but actually I haven't put it in the slides. Okay, so let's see, how do we actually get to fuzzballs? If you can actually convert the collapsing star to fuzzballs, then you are okay, because after that you just radiate like a piece of coke. Okay, so we did this. And so now our next question was, okay, so this is just to summarize what we've learned so far. There are just two orthogonal answers to the whole problem. Either you completely corrupt the horizon, break the no-head theorem, And that means around the horizon, you don't actually have a vacuum region. So this was the old picture of the black hole. It is around the horizon, whatever wave function you have is just the vacuum. So its overlap with the vacuum is 1 up to small corrections. We talked yesterday about the possibility of small corrections, and then we proved that small corrections actually cannot solve the problem. So this is the old picture of the black hole. And now we are saying that the overlap with the vacuum is certainly nowhere near the vacuum. We completely change the whole thing. So it's either 0 or something very small. This is what you would call, if you have this for all the states of the black hole, you'd say you're doing the fuzzball game. And if you have this, then you're doing not the fuzzballs. But of course, as we saw from the small correction theorem, the epsilon itself can't help you solve the entanglement problem. So if you believe in this, then you need some non-locality to get your information out, or to break the entanglement from here all the way to infinity, and then you need these long wormholes, or something new physics you have to do. These are just two answers to the problem. Okay, so how did the semiclassical approximation get validated so dramatically? And that was really the whole story for black holes, that this is what we want, but if you take a star, put in the computer, it seems to completely go in here, and then you get the pair creation, and you can't break anything. So this is a very basic point. In quantum gravity, when do you break the semiclassical approximation? So normally we thought there was only one place it breaks, and that is when the curvature scale becomes order Planck. Right? So if you have a manifold which is smooth, you would think that it has to be semiclassical. And once the manifold becomes very highly curved, so if a manifold has gentle curvature, it's semiclassical, and if someplace I make a curvature whose size is Planck length, then quantum gravity has to come. If this is the only way semiclassical approximation broke, and the quantum gravity only came in when the curvature became Planck scale, like happens at the center of the black hole, but here everybody agrees quantum gravity will break, you cannot solve it. What we're going to find is, there's one second way where the semiclassical approximation breaks. The second breakdown of semiclassical approximation, and that's the one which happens here. So we're going to see that semiclassical approximation breaks for a completely different reason also in string theory. And that breakdown comes not when you make a singularity, which is a high curvature story, but when you try to make a horizon. Anytime something is trying to come into a region where things are so compressed that light cones are in danger of turning over, something will happen and it will stop that process from happening. So it's a completely different breakdown of the semiclassical approximation, and let's see why that should be.
Can you just say a little more precisely what do you mean by semiclassical? You mean that you will do just perturbation theory in gravity and do
That's what
quantum
semiclassical.
field theory?
Yeah, semiclassical means that you take a smooth background and then do quantum fields on curved space, and that's the one which got us the pair creation method, right? So the whole structure has to change, not by order epsilon as we saw, but by order 1. The whole thing has to change completely, and the question is what makes it do that?
And the breakdown would mean that there would be some non-perturbatory effect which will come into, or something else?
So breakdown means that, for example, you have to convert this metric with its small quantum fluctuations all the way to something like this. Right now we just want to know why it would break. What we hope to get, we already know on the other side, because one by one we look at all the states and we know the exact construction of all the states. But how do we get from here to here? Why would a collapsing star go here and not just go here? You could have those states, but if you can't go to them, then what's the use of it? Yes.
Is it sensible to ask about quantum bound states?
Quantum bound states inside the fuzzballs? Well, in a sense, this is exactly what they are. If you look at what these fuzzballs are, that's exactly the word I would use for them. These are the quantum bound states of, let's say, D1, D5 brains. So if you take some brains in string theory, and you make their quantum bound states, the number of those bound states we already know agrees with Becker's entropy. That was the work of Strominger and Waffa. And now we are asking for the spatial extent of the wave function of the quantum bound states of D1 and D5 brains. And so the whole question is, will it increase the number of brains in a bound state? Typically somebody asked you what's the size of a bound state in string theory, the default answer would be maybe Planck size, or maybe string size, LP or LS. That's the only natural scale. But you can see what I'm asking you now. If I just took a bound state of 2 or 3 brains, there's no other scale. So you can say maybe LP, Planck length, or string length. But now if I say I'm going to put 1,000 brains in the bound state, you have a question to answer. Because either it's just Planck length still, or maybe it's 1,000 Planck length. You don't know, right? If you remain the size Planck length, the bound state, regardless of how many particles I put in, you would actually be in this situation. Right? If the size of the bound state became 1,000 Planck lengths, like kept increasing with the number that you put in, then you will here. Right? Because then it's as big as the horizon, it doesn't have to collapse. So what you really find in string theory, the size of the bound state increases with the number of particles. So a priori you didn't know the answer to it either way. You do the calculation, that's the size of the size. That's where it goes. So exactly, these guys are the bound states. And what you want to ask is what is their nature. Is it okay? Does that answer your question? Okay, so what makes a semi-classical approximation? So here is a shell which I have drawn, which is trying to collapse to make a black hole. And if it just went inside its own horizon smoothly like you would think, that's this picture over here, then the light cone would turn over and you have a problem, and we are trying to ask why that should happen. So now, as you take this collapsing shell, let's ask the question about tunneling, which was asked a moment before. Is it amplitude for this guy to tunnel into one of these first pulse states which I drew? I'm just writing its capacity, one of the states of the kind that you solved, all this thing, pinching and so on. And it turns out there is indeed a path. When you take two different gravitational solutions, there typically is a path to tunnel from one to the other, even if the topology is changing. So we want to just estimate the amplitude for tunneling from one to the other. As long as there's a path, you can crudely estimate the amplitude. So let's do that and see if it does anything for us. And as you might expect, the amplitude for tunneling is very small. Because if you have one macroscopic thing weighing like as much as a star, go to another configuration of the same mass, which is quite different, there will be an amplitude, but it will be very small. How do you estimate the small amplitude? The amplitude of tunneling is given by e to the minus s tunnel, and the s is just the classical action to go from here to here. Okay, so let's make a crude estimate. Let's just do it on the grounds of units. So the Einstein action is 1 over 16 pi g. I'm not writing about 16s and pi's right now. And then r d4x, that's the Einstein action. If I can compute the action of the process, then e to the minus the action gives me the amplitude for tunneling. Okay, let's just estimate the action.
The solutions are known, these tunneling solutions?
You can show the path. See, the solution is more than the path, right? The path just shows that I can find some topological paths to go from here to here. The minimal path should take me, we don't know. I don't know the solution, that's why I'm doing a crude estimate. I will say something about the minimal paths later when we borrow from the work of Krauss and Wilczek, but okay, that's not on this slide. So let's just estimate everything. The only length scale involved in the whole thing is GM, 2GM, I'm just calling it GM, there's no factor of 2. Okay, so then let's put in all the units. So there's 1 over G from the action is 1 over G. The R is 1 over length squared. Right? So all length scales are put as GM, so it's GM whole squared. The D4X, the whole thing takes place in a space and time region of size GM. So for that I put GM4. And please check, this is 1G and 2 powers of M squared. It's actually a big number because G is 1 over M Planck squared. So this is really like M over M Planck whole squared. So mass of sun in Planck units is about 10 to the 38. So it's 10 to the 38 square. It's 10 to the like 70 something. And so the amplitude for tunneling is e to the minus 10 to the 70. Very small. Why should you worry about it? There's always a small classical action, a small action for tunneling of even a macroscopic person like me through the wall to go to the other room. But of course I don't worry about it because it's very small. Why am I worrying about it now? The reason we're worrying about it is that in the last line over here. If you can tunnel to one fuzzball, of course you can tunnel to a different fuzzball. There are many, many different fuzzballs. And now we come to the one magical number about black holes that we have known for a very long time, but we never knew what to do with it. And that's the Beckstein entropy of the black hole. So the black hole has a very large entropy given by the surface area measured in units of Planck length square. And that number is huge. It's much more than the entropy of the sun with the same mass. So if you make a black hole out of the sun, it has much more entropy than the entropy you can get from ordinary matter, like just gas particles or anything. So if something has this large an entropy, that's very characteristic of what a black hole is. And you can see if I have the property of tunneling to one state, but and I know the number, it's the mod square of this A, I have to then multiply it by all the possible final states that I can possibly tunnel to. So this is what you do in quantum field theory in a scattering process. You multiply by the number of final states to see the total scattering cross section. So I'm really going to multiply this by the number of states I have, and the number of states is exponential of the Beckstein entropy because the Beckstein entropy is the number of states. Is a log of the number of states, so I have to e to the s Beckstein. But let's see what's the Beckstein entropy. So let me see if I can just do that in the same units on this side of the board. So the Beckstein entropy, the s Beckstein, is the area upon 4g, and again the 4s I'm not going to keep track of. The area is 4 pi times the horizon radius, gm, sorry 2gm, and I square it, 4 pi r square, and then I have to put the 4g, okay, I still have the 4, so let me keep it. So this comes out to be equal to, the 4 cancels, it's a 4 from these twos, 4 pi g square m square, but 1g is gone. Okay, so the Beckstein entropy is, if I don't look at the 4s and so on, it is a plus gm square. So do you see the beauty of this? This wouldn't happen for anything like the sun because the entropy here is very low. So for a macroscopic object, the tunneling amplitude is very small, and the entropy, the number of possible states, of course, you all have to multiply by the number of possible states you can go to. That's hardly anything. But now you see for the black hole, because this magical number, the very large Beckstein entropy, it can actually cancel the smallest of tunneling amplitude, and if these two factors cancel, now you see the process is not classical anymore. As you start coming in close to the to a particular radius, the smaller you shrink, the easier it is to start tunneling to these other guys. Because if instead of like 2 GM, suppose I put 4 GM, then this action will increase, right? These length scales will increase, there are more lengths up than down, and this will become more by a factor of 4. When I have two exponentials, two huge exponentials, they're really competing very strongly. One is a growing exponential, one is a decaying exponential. If I'm at 4m squared, like outside the horizon, this suppression here is so much more than the gain I get from here, it's completely gone. Right? So at 4m nothing will happen, 3m nothing will happen. At some critical point, this exponential will exactly equal that exponential, because that one is decreasing with the size as you come in, and this one is whatever the number is. Whenever the two exponentials cross, because there's such enormous exponentials, e to the power a huge number, immediately this guy wins over that guy, and you immediately have to turn it over to the first ball where probably it's gone, becomes number 1. So the good picture one is making is the following. One can reinterpret the physics that we are talking about in the following way. If you just want to see how this Semiclassical approximation breaks, just look at the path. This is a partition function. You do sum over all metrics, and you have to then put the action. So it is the way you do path integers for anything, so the same way you do it for gravity. So how do we get a semiclassical approximation? We say the measure is a quantum thing. We take this action and we extremize it because of 1 over h bar here, the h bar is small, so you get a classical approximation when this s has the minimum value. Right? So that's how you get the Lagrangian equation of motion. But we've always been ignoring this, of course. But what is the measure? The measure tells you how many quantum states are involved in the process. And that's normally something which is order 1, and this one had a 1 over h bar in it, and so you ignore the measure when you're doing the classical linear order approximation, and the next approximation the measure would come. But for black holes, the number of states involved is not small. If you actually look at the number of states is the e to the entropy. If you look at how the entropy of a black hole comes, it's actually a over 4g, and if you put back the h bars, there's a g in the denominator, there's an h bar in the denominator. You should really think of g, the coupling constant, as an h bar. So the reason the entropy of a black hole is so big is that it really is a 1 over h bar. It's a quantum effect. So if the entropy also has a quantum effect, what we found is the measure of the path integral for black holes is as big as the classical term. So that's just a reinterpretation of what I had on this picture, why the numbers are green. If you want to see the path integral language, this is comparable to this for a black hole because the Beckstein entropy is so big. And if in any problem, if this was comparable to this, you would not simply extremize this and say that is your answer. And that's the mistake we have been making all these years with the semiclassical approximation. We simply extremize the classical action, we ignored the measure, we knew the Beckstein entropy was so big, so we knew the measure was so big, and this crude calculation of the last slide shows you they are comparable. And so why should we have been extremizing the S? If you do that, do it at your own peril. It can't justify. So then what's the picture one has? And we'll draw a picture again. The picture is as a shell is trying to come in, it slightly has a leakage tunneling to any of these fuzzball things in the actual eigenstates and so on. But as you come really close to 2m, that rate of tunneling to those guys absolutely increases. By the time you come to 2m plus n blank, it's basically completely washed out of the fuzzballs, and there's nothing left to go inside. Yes?
So in this picture, at every point at infinity, you've got a compact direction. And in the picture before collapse, presumably you didn't. So does that mean that the topology is affected such that there's...
Topology has altered, absolutely. So you're changing from one topology to the other topology.
But it's changed over all of space. I mean, the
No,
topology
not
is a
all of
non-local
space.
thing.
No, the topology from infinity is actually trivial. So if you just look at the thing which I just showed you there, at infinity it is still R3 cross S1. So it's not like you change the topology at infinity. That you cannot do.
Okay.
Right? So if I'm making monopoles and anti-monopoles here, KK monopoles and anti-monopoles, the number of monopoles and anti-monopoles has to total up. And they have to be exactly equal. Because I can create no net monopole charge.
So there was an S1 to start with in the picture.
Oh, there was an S1 to start with. Absolutely. So if I only had 3 plus 1 canonically quantized gravity, I don't get any fuzzballs. The no-head theorem is correct, and remnants are the only answer. Or information losses are the only answer. Absolutely. If you have these compact circles, now we are in string theory. I was working specifically with the D1, D5P system. I have 5 compact dimensions. I start looking at their wave functions, and they are doing this. So this is what comes out of it. But then I have my compact dimensions. You can just see what they're doing. And nowadays you can look at the very complicated solution made by Bina, Water, and collaborators, and can see, this circle is doing this, circle is doing all the topologies are, and everything. There's one more example I want to mention here in case somebody is familiar with that. Are you guys familiar with Witten's bubble of nothing? Has somebody heard about this? Okay, it's a very interesting idea that Witten had. If you know 3 plus 1 Minkowski space is obviously stable. If you have 3 plus 1 Minkowski space with one extra circle, just a constant circle everywhere, Witten showed it was not stable. So why is it not stable? It's not stable because it can tunnel to something. So what does it tunnel to? Well, very similar to what I had here. You cut out a ball from the middle of this room, you throw it away, and then from every angular direction, the extra circle comes to the ball and pinches off. So very similar to what I just drew. Just the coefficients are a little different. It just comes and pinches off. And this makes a bubble of nothing. And then if you take the coefficient metric function, it's a bit different from what I showed. And then he showed that the space-time can, by fluctuation, circle somewhere can just pinch to 0, create a little hole, and then the hole starts expanding, and it keeps expanding, approaching the speed of light. That's called the instability of Minkowski space, tunneling into the bubble of nothing. That needs an extra compact circle. It doesn't work if they are fermions, because fermions get the wrong boundary condition there and so on. So that's why people never took it too seriously. But it's an instability of Minkowski space with an extra compact circle. So you know there also you have the same topology change. You go to something very much with the topology of what I drew for Euclidean short-chain here, starting with M3,1 cross S1. So just that same instability which took you there, in the case of black holes, you're getting a similar problem, but there are different solutions. These have a mass, and they stabilize at some size. So the only philosophy of tunneling is common maybe, but everything else might be different. Yes?
I'm confused. Are you putting in from the beginning that the black hole has a large entropy? Or does it arise during the collapse? Like, how does the star know that it has to start increasing its...
Okay, good question, yes. So, no, I'm not putting in the fact that there were many states to start with. I'm putting in the following. When I actually solve for all the states with a given energy, I'm putting in the fact that I have all these first-pass solutions, so they are into the S states of size roughly 2m plus a little bit, and those are my eigenstates, and those I first check that they are in my theory. Now I start with a big shell of large radius, which is just an ordinary piece of dust or matter or gravitons, doesn't matter, there's nothing there. And as these gravitons come inside, I just ask if there are some other direction in my configuration space. Classically, I would not explore that, but quantum mechanically I have some amplitude for leaking into that direction. So I just estimate the amplitude for leaking into that direction as the shell is coming in. I can go leak into that particular configuration if that configuration exists. So if I didn't have string theory, only 3 plus 1 gravity, that configuration doesn't exist, I'm not going to leak into anything. Then my shell will just keep going in, come to the horizon, keep going further in, go to a point. But any radius I find there are alternative solutions of gravity possible, I have some amplitude for going into those guys. If there are many of those guys, alternative solutions, I have a lot of amplitude for leaking from the shell to something else.
But suppose our collapsing mass is just above or just below the limit to become a black hole, like how does...
Okay, if it below
if
the limit to become a black hole,
it's going to become a black hole. If not, it's going to become a neutron star.
good.
What's...
So that's where this balance came in. Suppose I had a size for the ball where instead of getting it down to size 2 gm, suppose it was at 6 gm. Then these numbers will get an extra factor of 3 squared. There will be a 9 here. Okay? And suppose these exponentials were just matching when the size became 2 gm. If I put an extra factor of 9 in one of them, then this exponential is e to the minus 9 times that number, and this doesn't have the factor of 9. This is completely killed compared to this, and nothing. So if you make a neutron star, which is off from this by a factor of 3 from the black hole, the probability is really 0 for it to see any of these effects. It's only when the two numbers are exactly clashing, as you come in. At some place the two exponentials have to cross, and by default you can call that the place where the horizon is, or where the new physics happens. So in some sense, wherever the entropy crosses the action, there'll be a certain change. And that's, you can call that the black hole size. Anything bigger than that, it dries so fast, you'll never see anything.
So if you could know the precise number of these first balls, then you could predict the black hole.
So the number of these guys, you probably can always say is going to be e to the s biggest, right? So because then the black hole will behave very well. It is this part which is harder to do, right? The tunneling amplitude. But in fact, what we wrote another paper after this, where we showed using the work of Cross and Wilczek, or something with Cross, where they actually computed tunneling amplitude for a shell to go for shells to tunnel from one configuration to another. And it turns out it's actually given by exactly e to the minus s biggest. So it was a little unclear what amplitude represents because it was an abstract calculation. But in fact, if you believe that, it's exactly e to the minus aspect. It's exactly cross. And then what has been done after that is some nice work with by Veena and collaborators last year, I think, where they actually took some fuzzball solutions and completed tunneling from one fuzzball to the other, not from a shell to a fuzzball, but a bigger fuzzball to a smaller fuzzball, and they saw the entropy enhancement. So you can see the entropy enhancement directly with a full string theory calculation. So bits and pieces are known, but if you exactly ask me to do this for a generic shell to a generic fuzzball for short shell, we are not interested. So it's just an argument you put over everything to see how it could ever make sense.
You could have, let's say, started with a star, which is just below, it has mass just below the point where it can't hold any longer.
Okay.
Now that will remain a star as such, right?
Yes.
Or could it also tunnel into some fuzzball-like thing? Is there some probability to tunnel? If it's just below, let's say some few Planck masses below.
Yeah, I think there's a bit of a hysteresis in this thing. Like a star which is just about to support itself
Yeah.
by normal means
Yeah.
would probably satisfy the Bookdor's theorem. So it'll have to be bigger than 2 1/4 m. It'll sort of, if you're just supporting it by normal pressures, it'll have to be bigger than 2.25 m, like I showed you earlier.
Uh-huh.
At that place, is almost no tunneling to anything. If you let it further collapse and come at with 2.2 m, not 2.25 m, then the ordinary pressure won't support it. So it'll keep going in. Except when you come to 2 m plus 10 Planck length, this other process starts where you're going into the huge number of fuzzballs, and then the guy just turns to fuzzballs and will probably stabilize at that size. This would be my picture, but it's only a picture.
And if it was like just to stay in these fuzzball things and not evaporate, even then there would have been like entropy violation thing, right? Because you could have started with initial thing which was pure, and you ended up into something which has a lot of entropy.
No, that's not a violation. No, let me disagree with that. If you just take, let's say, some atoms in this room and keep them in a corner, and that's the pure state, and then I just let them go and they spread all over the room, I would say, but they're not interacting with the outside, that is still a pure state for me, and the entropy is still 0. If I coarse grain by averaging it with other states of the similar kind, I can attribute an entropy to it, but it remains a pure state. But the same is happening here. If I start with a shell, which is a definite state, it has some amplitude tunnel into every fuzzball, but only one particular linear combination of fuzzballs.
Oh.
And the actual linear combination of fuzzballs you get exactly has the information of which shell I started with, and a different shell will go to a different linear combination. It's complete.
Okay.
It's exactly like taking particles in a corner of the room with low entropy and letting them spread all over the rest of the room. There's no real entropy increase or dissipation or anything really. It's a completely unitary process. It's just change of structure. So that's very important. We have never introduced any new physics anywhere. There's no new non-local physics. There is no violation of quantum theory. There's no nonlinear quantum mechanics. It's just string theory taking care of itself by making sure that closed trapped surfaces, light cones turned over. It's a little bit like what you might have seen in the conifold transition, if somebody is familiar with that. Suppose there's a cycle which is pinching in a Calabi or manifold. Then new brains can appear which wrap that cycle, because now they can become very light. And they modify the dynamics and prevent the simple shrinkage of that cycle. So whenever some new thing can come in, when something is about to happen, it can change the physics. And that's what we are seeing. As you start approaching a horizon happening, the large number of alternative fuzzball solutions, their measure comes and prevents the further continuing inside the horizon. So that's the second mode of breakdown of quantum gravity, of classical gravity that I was talking about. Either the curvature becomes high, but there is no entropy, or the curvature remains low, but the entropy of possible solutions is so large, it's the Bekenstein value, that brings us. So this second breakdown of semiclassical approximation is what I'm arguing in string theory would actually resolve. So I'm basically out of time, so let me just close with a summary slide. So if you, there are so many people giving you so many different solutions to the information problem, but I want all of you to become experts in this problem from the moment you leave the room. And an expert is a person who only asks 2 questions. So if anybody comes to you with a solution, you please ask him the following questions. Firstly, in your model, is there a mechanism to break the Noether theorem? As we saw, Noether theorem is not easy to break. There's so much pressure that things want to just fall in. In fact, the Bookdor's theorem tells you if you come anywhere close to horizon size, anything like a simple fluid or any variable, there are lots of variants of Bookdor's theorem now, you have to go in. It will be very non-trivial to break that theorem. And it's not only classical, the vacuum also cleans out because you can't support any modes on it. The vacuum becomes the vacuum, the ordinary vacuum, and the classical physics is also just the vacuum. So how do you break the Noether theorem? And if somebody hasn't come to you saying, I'm using string theory or this theory, I'm just arguing abstractly in 3 plus 1 dimensional gravity, and string theory may just do something if it wants to. He actually cannot break the Loher theorem. You got to ask him the first question. And if he doesn't break the Loher theorem, then what happens to the entanglement of the produced pair? When you produce the entangled pairs, and as we have seen, he could come and tell you, I have small corrections from quantum effects, but small corrections, as we saw, don't help. That's the whole debate we had over the last 5 years of the strong certain theorem. The small corrections are going to fix your problem. So either you break the Loher theorem, and then it's like a piece of coal, or you have the vacuum with which is vacuum of leading order. I just put the epsilon there because leading order effect is there. And now you do something like new physics, and I'm putting in new physics all the things like non-local things and wormholes and anything you do which is breaking either causality or locality or anything. So I don't know those effects in string theory. I have never seen an actual effect in string theory which is non-local or a-cause. But they could be there. So there are people like Giddings who would argue there is some non-local effect which it takes you from here to here, or people argue that you can go very far away and break something. So there are many alternatives that you could try to have, but then you need those. So everything falls into 2 categories. You either have to break the Loher theorem and then you have no problems. Just call it the fuzzball cutting, and string theory seems to do that. And then you have all the other things you could do. And then you're going to ask these people, can you really find that effect, and are you actually breaking causality? So locality and causality for me are actually very closely connected. Why do you get, if you can't travel faster than the speed of light, you can't have action at a distance. This was an old debate from the early 50s. Can you have action at a distance in physics? So actually, finally people conclude you can't. How do 2 things interact? If I have to interact with you, let's say electromagnetically or gravitationally, I emit a photon, the photon travels there at the speed of light, and then hits you, and that's the force you feel. And that's why, because the photon can't go faster than the speed of light, you actually can't have instantaneous action at a distance. So if you have to have locality, like I have to emit, if you want to have causality, something go faster than the speed of light, it goes hand in hand with causality. That causality means you can't go faster than the speed of light, but locality tells you that I emit a particle here. Only when that particle goes to you and interacts with you locally, then you're going to feel the effect. So in some sense, these 2 things are really 2 sides of the same coin, locality and causality, for me. And I think string theory actually preserves both of them. You can have a long object like a string, it will look like a non-local object. The physics is local. I vibrate this end, it moves at the speed of light, and then it vibrates the other. So just having a big object, you could even have a string in your home, but that doesn't mean that the physics is non-local. So if you have locality and causality, then I think all these things are possible. And then I think this is the only thing possible. So I'm reminded of the 5 blue cars that Mathur was talking about yesterday. So suppose you have seen every car you've seen in life so far was blue. Are you entitled to believe that all the remaining cars of the world will be blue? Well, that's roughly the situation with fuzzballs, because people have been now making them for 20 years. And every case that we have made with any bound state in string theory has always been of this kind, not of that kind. So in some sense, all the cars you've seen so far are blue. But we haven't seen all the cars because there are lots of other black holes like the Schwarzschild black holes and so on. And the fuzzball conjecture is just saying that all the other cars are also blue. Okay, so let me just start.
More questions for Samir?
Yes, please.
So suppose we didn't know anything about string theory or higher dimensions and all that, but we thought deeply about information paradox or Schwarzschild. Would we have discovered string theory this way? Like we said, we need to have extra dimensions because we need to have fuzzballs. That means we need big brains, or
You could have. I think the real problem is that you cannot rule out the remnants very easily. And the reason for that we saw yesterday, that you actually, once you have a horizon, inside the horizon is an infinite amount of space, because R equal to constant of space like slice. So if you just put particles inside there, they can stay there. Right? So you can actually fit an infinite number of particles in a finite mass bound, because the light cone has turned over, and that's what you would like to call it. And if that's where you naturally end up at the evaporation process, why wouldn't you just take that and stop it? It is funny in the sense that with a finite mass bound, you have an infinitely many states, and normally that's not allowed. But here, because time has changed sign, energy doesn't have the same meaning as before. That's really the reason why with a given energy you can have many states. The meaning of energy changed because R became T instead of T becoming R, remaining T. And so if your theory allows you to break the normal belief that with a finite energy you can have only a finite number of states, why wouldn't we just take that solution? And that's what the GR people do. It's very hard to convince somebody who already has something which is consistent It has lots of other problems, like when you go in loops, you have to imagine they don't couple very strongly. At least the more complicated elements couple weaker and weaker. But you can sort of imagine that the deeper you put them in the slice, you can say you couple more weakly because you can't like grab it, right? So you can always make models which work. When you start with a theory which is from first principles, then below Planck energy you really won't have too many states. That's what happens in string theory. Below Planck mass you only have 5 deep and then 1 elementary string and then whatever you have, there's nothing there. And then once you have ADS CFT, even if you make bound states and now you say, okay, there's gravitational attraction that could lower the energy. That's how all this, you got this trouble, right? And you may say, okay, the attraction will be so strong that I don't know what it's doing, and so on. But then if you have ADS CFT, all that is good. So, I mean, you still can't get too many states on a given energy, so the number of states is finite. But once you have these facts and all those options are gone, then I think you're in the first place.
You said that you can start with any arbitrary state and eventually turn into this kind of fuzzball thing. But each of these fuzzballs would reproduce the same Hawking radiation, right? They would all, given if they have same mass, they all produce same Hawking radiation.
So not same, that's a very important thing. So if you take two different pieces of code, to leading order, roughly it's the same spectrum, but the spectrum has imprinted on it the difference in the different pieces of code, because obviously it has to carry the details of where the atoms are.
So where do you say Hawking's calculation is wrong in?
Yeah, so that's exactly what happens here. That's why it's so beautiful. If I take two of these different JMAT solutions, each JMAT solution comes with several different parameters. There are many different rotations, and orbifold like the next was one JMAT thing. So there will be one solution which is like this, and one solution which may be like this. And you just draw them schematically. None of them has a horizon. But this guy radiates atoms in some way, and this guy radiates atoms, gravitons in a different way. And if you get the entire emission spectrum from this, and the entire emission spectrum from this, it actually corresponds to carrying the information about the structure was in here. So in what sense does it actually match on to Hawking radiation? Well, that we have seen actually one step before in the mid-90s. On the gravity side, you have this black hole which creates pairs, so you have only one answer, you just see a thermal distribution. But in string theory, we had these D-branes, which you can excite by putting vibrations on them. And just like if you have a vibrating string, which can emit sound, like a guitar string, the waves on the strings collided and emitted gravitons. So this was an emission calculation from D-branes, and this was the black hole calculation. And as you might remember, if you know the work from the mid-90s, these two exactly emit. So if you put a generic thermal distribution here of vibrations, it emits at exactly the rate that you get from this Hawking calculation. But you see, actually this doesn't make any sense, because here you could, the information is there, you could put not the generic one, but some very special ones. We can put all the quanta in some particular state rather than spread on thermal distribution. For any distribution here, the emission is going to be a little different. It's just not a mechanical system. If you put a thermal distribution, it will agree with this. You put some other, you get another answer. So now what you do is you go here and you put some other one, the non-generic one that corresponds to the JMAT solution. You get the emission for that guy, it's a calculation. The same one that gives Hawking radiation. You do the calculation here, you find exactly the same. So state by state, you keep putting different things here, you keep getting different emissions here, and they exactly agree. So these are exactly astronomy of our first states, special ones. Emission of each of them agrees with this, not having any information. You put a generic one, it agrees with this. So the picture would be a generic, first one would just be like very messy, and then you put generic things here, and the radiation from this guy will be exactly back to Hawking. But at no stage have you actually done the pair creation thing, and so you don't actually have it.
There are like very special of these things which won't emit like Hawking.
Yeah, so any special guy never emits like Hawking, right? If I gave you a piece of core which is, let's say, an exact crystal, it will only emit at the frequency of vibration of the crystal. It won't actually go into a complete generic spectrum. That's maybe the answer here.
And they would like look, in terms of gravity solution, they would look different from...
They do, yes, because I've taken a very special one.
There are no black hole whatsoever, even no extremal black holes.
So extremal is only a matter of charge being equal to mass, right? So all these solutions, you can take ones which have charge equal to mass, not the JMAT ones. You can take with charge equal to mass. None of them have a horizon. The very special ones will look nowhere near the black hole. The generic ones will look like a black hole for most of their structure, like far out and then close to where the horizon would have been. If the horizon was supposed to come here, it would basically look the same here, but then out here. Generic ones are like, non-generic ones may just come and close here. That's like the ones I'm just like. It's the non-generic ones that are easier to play with for obvious reasons. But they're easier to make. By non-generic, I mean you take the ones that actual side. So easier to take. But the generic ones will basically come right up to here and do this. But if that's, for two charges, you can solve everything. That's what you see. Generic ones are doing this. But you see, often play with just these guys, much easier to play with them and get your intuition. Just see the other ones.
Okay, so we'll finish here, and Samir can answer questions in private if people have them. Costas is the next speaker.